Now let's consider molecules, whether homoatomic or heteroatomic. We said in an earlier lecture that, for instance, oxygen gas is made up of diatomic molecules that consist of two oxygen atoms connected by a covalent double bond. Because an oxygen molecule is made of two oxygen atoms, the mass of this molecule is the sum of the masses of the two atoms. In the periodic table, we can find that the atomic mass of oxygen is 15.999 atomic mass units. Then the mass of an oxygen molecule, referred to as its molecular mass, is 15.999 atomic mass units plus 15.999 atomic mass units, or 31.998 atomic mass units. Let's say we have a sample of oxygen gas with a mass of 4.92 grams. How many oxygen molecules are there in this sample? To find out, we first convert the mass of the oxygen molecule from atomic mass units to grams. One atomic mass unit is equal to 1.660539040 times 10 to the minus 27th power kilograms. So 31.998 atomic mass units is 31.998 times the value of an atomic mass unit in kilograms, and that equals to 5.3134 times 10 to the minus 26 power kilograms. And because 1 kilogram is equal to 1000 grams, 5.3134 times 10 to the minus 26 power kilogram is 5.3134 times 10 to the minus 23rd power grams. The mass of the oxygen gas sample is the sum of the masses of all the identical oxygen molecules that make it up. The mass of the sample, therefore, is the number of molecules multiplied by the mass of one molecule. Therefore, we can find the number of molecules of oxygen by dividing the mass of the oxygen sample by the mass of one oxygen molecule. The number of molecules is the mass of the sample divided by the mass of one molecule, and when we plug in the numbers, we get 4.92 grams, the mass of our sample, divided by 5.3134 times 10 to the minus 23rd power grams. That's the mass of one molecule. And the result is 9.26 times 10 to the 22nd power oxygen molecules, where we have taken the correct number of significant digits. This number is very large, but just like atoms, molecules can also be counted in moles. To express the number of oxygen molecules in moles, we divide it by the number of molecules in 1 mole of molecules. So the number of moles of oxygen molecules is 9.26 times 10 to the 22nd power oxygen molecules divided by Avogadro's number. When we do the calculation, we find that the answer is 0.154 moles of oxygen molecules, or 1.54 times 10 to the power minus 1 moles of oxygen molecules. There is, however, a simpler way for finding this number. We saw that for atoms of all elements, the numerical value of the atomic mass, expressed in atomic mass units, is equal to the numerical value of the molar mass expressed in grams per mole. Similarly, for molecules of all elemental substances and chemical compounds, the numerical value of the molecular mass, expressed in atomic mass units, is equal to the numerical value of the molar mass, that is, the mass of 1 mole of molecules, expressed in grams per mole. We can check that this is true for the oxygen molecule by multiplying the number of molecules in 1 mole, Avogadro's number, by the mass of one oxygen molecule in grams that we just found. When we multiply these two numbers, we get 31.998 grams per mole. So if one oxygen molecule has a mass of 31.998 atomic mass units, then 1 mole of oxygen molecules has a mass of 31.998 grams. Now, if this is true, we can calculate the number of moles of oxygen molecules in a sample of oxygen gas with a mass of 4.92 grams simply by dividing this total mass of the sample by the mass of 1 mole of oxygen molecules. That is the molar mass. And we get 1.54 times 10 to the minus first power moles of oxygen molecules. The same result that we got before, without having to deal with very large or very small numbers. Generally, the number of moles of atoms or molecules in a sample is equal to the total mass of the sample divided by the molar mass for the atoms or molecules out of which it is made up. The number of moles of atoms or molecules of a substance is referred to as the amount of substance. Let's also ask the following question. If our sample of oxygen gas consists of 1.54 times 10 to the minus first power moles of oxygen molecules, how many oxygen atoms are there in this sample? Because there are 2 oxygen atoms in every oxygen molecule, the total number of oxygen atoms in the sample is twice the number of oxygen molecules. Number of moles of oxygen atoms is number of moles of oxygen molecules times the number of oxygen atoms per oxygen molecule. So 1.54 times 10 to the minus first power moles times 2 oxygen atoms per molecule. And that gives us a value of 3.08 times 10 to the minus first power moles of oxygen atoms. When we talk about amounts of substance, we must always specify the number of moles of what exactly we calculated. Remember, 1 mole is just a number, 6.02214,129 times 10 to the 23rd power items. And we need to say what the items are. In the same way as we may have a dozen eggs or a dozen roses, and we need to specify a dozen of what we have. We may have a mole of atoms of various elements or a mole of molecules of various elemental substances or chemical compounds, and we need to specify a mole of what exactly we have. Now let's consider the example of methane, a molecular compound for which the molecule consists of 1 carbon atom and 4 hydrogen atoms. What is the molecular mass of methane? It is equal to the sum of the atomic masses for all the atoms that make it up. So the molecular mass of methane is the atomic mass of carbon plus 4 times the atomic mass of hydrogen, because there are 4 hydrogen atoms. And if we look at the periodic table and find the atomic masses for carbon and hydrogen, we will find that the molecular mass of methane is 16.043 atomic mass units. We have multiplied the atomic mass of hydrogen by 4 because we have 4 hydrogen atoms in the methane molecule. What is the molar mass of methane? It has the same numerical value as the molecular mass, but the units are grams per mole rather than atomic mass units. So it's 16.043 grams per mole. Let's say we have 25.045 grams of methane. How many moles of methane molecules do we have? The amount of methane is equal to the mass of the methane sample divided by the molar mass of methane. And that's 25.045 grams divided by 16.043 grams per mole, which gives us 1.5611 moles. How many moles of carbon atoms do we have in this sample of methane? Because there is 1 carbon atom in each methane molecule, there are 1.5611 moles of carbon atoms in 1.5611 moles of methane molecules. How many moles of hydrogen atoms do we have in this sample of methane? Pause the video for a moment and try to figure this out. Because there are 4 hydrogen atoms per methane molecule, the number of hydrogen atoms in this sample is 4 times greater than the number of methane molecules. 4 times 1.5611 moles of methane molecules gives us 6.2444 moles of hydrogen atoms. Ionic compounds do not consist of molecules. However, the mass of their simplest unit is commonly referred to as their molecular mass, and the mass of Avogadro's number of their simplest units is referred to as their molar mass. So because the simplest unit of sodium chloride, for example, consists of 1 sodium atom and 1 chlorine atom, the molecular mass for this compound is the sum of atomic masses of sodium and chlorine, 22.990 atomic mass units plus 35.453 atomic mass units, and that gives us 58.443 atomic mass units. The molar mass of this compound is then 58.443 grams per mole.